Andrea will be late, but she will come. Ya empezaste
Uh,
a podés
Andrea is
cortarla y
here
empezar de nuevo.
because I can't see. Yeah, I can't see the participants. You're saying that Andrea is here?
Andrea is going to be here in some minutes after
Okay.
she's taking an exam and hopefully will last.
Okay. So
It
she's
will
in
be
Buenos
short.
Aires now.
No, she's not. She's here in China, but she's on another Zoom meeting taking an exam.
Okay. Mm-hmm.
Oh, I'm very happy to welcome today's speaker, Samuel Lopes from the University of Porto, who's going to give us a talk titled on the Hochschild cohomology of quantum nilpotent algebras. Thank you very much, Samuel. You can begin whenever you're ready.
Okay, thank you very much, Franco, and all of you for being here and for the invitation. So, yo empiezo por decir que sería bueno que hablara en castellano, pero estoy un poquito, han sido unos días un poquito complicados, entonces estoy demasiado cansado para pensar matemáticas y lenguas al mismo tiempo, entonces voy a hablar en inglés, si está bien. Okay, so well, first, besides thanking the hosts, which I really do, and the participants. So first of all, what I'm going to talk about is work. It's joint work with my collaborator Stéphane Launois, currently in Caen, in France, and Isaac Oppong in Greenwich. And this is, so I mean, the paper is on the archive, although this is still ongoing work. I'll explain a little bit more at the end of my talk what we're working on next related to these things. I mean, it's part of something that we've been thinking about for a very long time. And some of the motivation comes from the following. So I've divided the talk into 5 moments. So you know what to expect, because I mean it's kind of I'll try to make it as painless as possible, but there's some technical moments in the middle, and so I thought it was better to divide it up. And so what's the motivation and what's the background? So one of the ideas is the following. So there's a very classical result of Dixmier that says that if you're interested in the representations of, or in the simple representations, the simple modules of a finite dimensional nilpotent Lie algebra, then you should really just be looking at the representations of the Weyl algebras. Okay. And the reason is that, so a representation of a Lie algebra is the same thing as a representation of its enveloping algebra. And when you have the representation of the enveloping algebra of a nilpotent Lie algebra, if it's a simple representation, and if you look at the kernel of the representation, so the things that act as zero, so they're completely irrelevant from the point of view of the representation, and you quotient by that, you always get a Weyl algebra. Okay, so these will always be representations of Weyl algebras, and conversely, given a Weyl algebra and a representation of this Weyl algebra, we can always construct a nilpotent Lie algebra that admits that as a simple representation for the corresponding nilpotent Lie algebra. So that's the point. So I mean, in more technical terms, this is saying that the primitive quotients of the enveloping algebras of nilpotent Lie algebras are the Weyl algebras. Okay, and so the Weyl algebras are very. I guess I could have had some for I don't know if all of you are familiar with the Weyl algebra. So for example, the first Weyl algebra is just the algebra of differential operators on the line. And by line, I mean just a one-dimensional, the polynomial algebra in one variable. Okay, so if you think of 2 operations on the polynomial algebra in one variable, one is multiplication by that variable, the other one is taking the derivative with respect to this variable. These 2 operations do not commute, and they're actually at the heart of the Heisenberg uncertainty principle. This non-commutation of observables and momentum position and momentum. And so these two operators don't commute, and they satisfy the relation that the commutator of one with the other. So if I call one of these operations x, the other operation y, I get the relation that y times x minus x times y is equal to the identity. Okay, and this is the defining relation for the first Weyl algebra. So the larger Weyl algebras, AK, you can think of them in two ways. One is, I mean, you just take the tensor product of the first Weyl algebra with itself, and you get the kth Weyl algebra if you do this k times. Or just the same thing, you can just consider polynomials in k variables, let's say x1 up to xk, and you consider the corresponding partial derivatives with respect to these variables. So partial with respect to y1, to x1, x2, xk. And if I call these operations yk, the partial derivatives, then I get the corresponding relations that say y3 commutes with x3, with x2 and x4 and all of the different x's, but it does not commute with x3. And these two operations satisfy exactly the same commutation relation that I said before. So, for example, y3 x3 is equal to x3 y3 plus the identity. Okay? And this is what defines the Weyl algebra. So it's a very interesting object. It's an infinite dimensional algebra, associative algebra with a unit. It has even Gelfand-Kirchhoff dimension. So this kind of measures, since it's not finite dimensional, we have to, use measures of growth that go beyond dimension. And one of the typical dimensions that one computes is the Gelfand-Kirchhoff dimension. So it has even Gelfand-Kirchhoff dimension. I'm pointing this out because evenness here is kind of interesting, important, and symptomatic, because it kind of, in a certain sense, it comes from the geometry, because this really comes from quantum physics and quantum Hamiltonian systems, and those are related to Poisson geometry, symplectic and Poisson geometry, and there you need even dimensions. So this is kind of the algebraic reflection of that. And from the point of view of cohomology, it has trivial Hochschild cohomology. By the way, I will forget to say it. I will be talking about characteristics. When I say these things about the Weyl algebras, this is in characteristic 0. Okay. For my talk, I have no requirements on the base field. It could have positive characteristic, but these general statements that I'm putting forth here are true in 0 characteristic. Okay, so if you want, you can always assume that I'm in characteristic 0. So these Weyl algebras are simple, so they have no ideals, they're Noetherian, they're domains, and they have trivial Hochschild cohomology. So that the center is just the scalars, and then everything else is 0. So in particular, they're rigid. Okay, and they're really, really very nice. They show up everywhere, and so if we want to kind of deform things a little bit, quantize things a little bit, so in general, there is no theory of kind of deforming the enveloping algebra of an arbitrary Lie algebra. But for certain kinds of algebras, there's a standard deformation. In particular, if you have a semi-simple, finite dimensional semi-simple Lie algebra, you can look at the standard Drinfeld-Jimbo quantum group associated to G, which is denoted by UQ of G. Okay, and as in the standard case, it has a triangular decomposition. So, for example, if you think of G as n by n matrices, if you want to trace 0. Then you can think of G plus as the strictly upper triangular matrices, G minus strictly lower triangular, and H the diagonal matrices. And this gives this tensor product decomposition of the enveloping algebra. So in the quantum case, you also have this triangular decomposition, and so you can think of the UQG plus and UQG minus, they're isomorphic. You can think of these as kind of deformations of this enveloping algebra of a nilpotent Lie algebra. We have a specific nilpotent Lie algebra. It's a nilpotent Lie algebra which appears as in the triangular decomposition of a semi-simple Lie algebra. Okay, so these algebras, as in the classical case, are essentially just given by the quantum Serre relations, which are just saying that if you consider the Chevalier generators, E1, E2, E3, and so forth, they're just saying that the adjoint maps are locally nilpotent. Okay, so if they're in this formula that you see, that thing that appears in square brackets were just a binomial coefficient, this would just be saying that add EJ acts locally nilpotently. Okay, this is it's in square brackets and has an index I, and that's because it's just a Q deformation of this binomial coefficient. So it's kind of a skewed version of the standard enveloping algebra of a nilpotent Lie algebra. Okay, so these are the relations that these things satisfy, and so when you quantize, sometimes you change kind of the flavor a little bit, and it is this kind of a personal view because it depends on what you're looking at. But in my view, for several things, I think UQG plus has more of a behavior of the enveloping algebra of a solvable Lie algebra rather than of a nilpotent Lie algebra. In particular, because contrary to the classical case, not every primitive ideal is maximal. So now, for these algebras, if you were looking at the quotients by the annihilator of a simple module, you would not always get a simple algebra like the Weyl algebra. Okay, but they have some things, and they have other things, and this is the case in general for the enveloping algebra of a solvable Lie algebra. This is why I'm saying it's more of that flavor. And also, like solvable Lie algebra, like enveloping algebra of a solvable Lie algebra, it can be presented in a certain way. It's called an OR extension. I'll say a little bit about that a little bit later with a little bit more detail. So the idea is, I mean, if in the classical case one retrieves the Weyl algebras just looking at primitive quotients of these enveloping algebras of nilpotent Lie algebras, the idea is that when we do this in the quantum case, we should get some kind of analogues of the Weyl algebras. Okay. Now, if we want to restrict to the case where the algebras are simple, then we cannot just take any primitive quotient because it might not be a maximal ideal. But we can take the simple quotients, which will in particular be primitive, and this has been looked at for a long time. So the simplest case is SL3. So and you look at the positive part, and this was called the Weyl. So if you just look at the positive part of SL3 in the quantum case, you get essentially a quantum Heisenberg Lie algebra. But then if you look at the infinite dimensional simple quotients, essentially you just get something that's called a Weyl-Hayashi algebra, which was studied by many a long time ago. If you look, for example, for the case of SO5, so V2, or which is simply a C2, if you prefer symplectic. And in that case, you will get the same Weyl-Hayashi algebra, but you get a couple more, a couple different algebras, which in fact are different. And you can look at type G2, and this was looked at recently by Stefan Launois and Isaac Oppong. And for that, they get certain families of primitive quotients with some properties that are somewhat, not completely analog of the properties of Weyl algebras. And a long time ago, I looked in general at the AN type, so at the case of SLN, and I constructed a bunch of simple quotients of the corresponding quantized enveloping algebra of the positive part. Okay, so these are some of the things that have been done, and so our idea is to, as I said, our motivation comes from trying to find these analogues of the Weyl algebra in the quantum case. I mean, there are many algebras which are called quantum Weyl algebras. We want to construct them via this way. So as we want to look at what kind of simple quotients can this this UQG plus have, and what are the properties of these algebras. Okay, so in particular, one interesting question, I'll explain in a second why I'm talking about this. One is interested in looking at the automorphism group of these algebras, and this was a conjecture, which is now a theorem, has been a theorem for a long time. It was called the Andruszkiewicz-Dumas conjecture, that the automorphism group of these UQG pluses was kind of small, essentially just given by the semi-simple automorphisms that are just scaling the Chevalier generators, plus coming from the diagram automorphisms of the Lie algebra. Okay, and this in fact has been proven in 2014 by Miller and Yakimov. Okay, so this says in particular that these algebras are very rigid. They don't have a lot of automorphism. They just have the obvious ones that you would expect. Nothing more. Okay, and previous attempts to prove this have used information about the prime ideals of these algebras and about the derivations of these algebras. Okay? So this again raises the question of, and this is really what we're interested in ultimately, is you need, the point would be to try to find these nice simple quotients of certain algebras, which include these UQG plus. Okay, think of them as analogues in the quantum world of Weyl algebras, and then you would expect them to have certain properties in common with Weyl algebras. In particular, one would want that their Hochschild cohomology be trivial. Okay, so this is our goal, and I'll tell you right away that we haven't achieved it yet. So we have achieved it partially, not for the simple quotients, but for the algebra itself. Okay, so for these UQG pluses and a certain larger class than this, a generalization of this class, we have managed to at least look in degree 0 and degree 1 for the Hochschild cohomology. And this is what I want to tell you about what the result is and what the methods were. But our ultimate goal is really to now push these kinds of results forward into the quotients, into simple quotients of these algebras. This is really what we're even more interested in. Okay, but I think the results here are still quite nice and I think interesting. So this is what I'm proposing to tell you. But so since we're looking at derivations, there is a connection between automorphisms and derivations. In case of a finite dimensional algebra, it's a very, very strong connection. In case of an infinite dimensional algebra, there's still a connection. It's a little bit less strong, but at least one way to go from derivations to automorphisms is if you start with a locally nilpotent derivation, so a derivation that, on a given element, a certain power of that derivation will be 0. Okay, then you can always exponentiate it, and you will always get an automorphism. Okay, and if you do this for all locally nilpotent derivations, you will get a normal subgroup of the automorphism group. Okay, now it turns out that since the automorphism group by the Andruszkiewicz-Dumas and Yakimov theorem, since the automorphism group is very small, you would expect that there aren't a lot of derivations. Okay, or even that there aren't a lot of locally nilpotent derivations. Okay, and in fact, it's true. It's actually not in our paper, but I can tell you that it's true. That one of the consequences of our work is that there exists no locally nilpotent derivations. So that doesn't give anything. Yet, what's interesting is that, you would expect, since I'm saying that it's a normal subgroup, of course, 0 is a normal, or the identity is a normal subgroup, but there's another obvious one coming from that conjecture, which is those diagonal automorphisms, so that those n copies of the non-zero scalars. So you would expect that maybe you would get that from the locally nilpotent derivations. You don't, but this I find very interesting is if you're working over a complete field, a field where Cauchy sequences converge, then you can exponentiate derivations which are not necessarily locally nilpotent. Okay, so we are able to find derivations which are not locally nilpotent, and over the reals of the complex numbers, we're able to get these automorphisms. But the point is that there are many, I mean, there are really way more automorphisms. So contrary to what happens in respect to the automorphism group, which is small, the Lie algebra of derivations and even the Lie algebra of outer derivations is quite large, okay, and quite interesting as a Lie algebra. Okay, so this is essentially the motivation for what I'm going to talk to you about. Which is coming from this setup, okay, of looking at these quantized versions of the positive part of the enveloping algebra of a semi-simple Lie algebra. Okay, so I don't know if there are any questions. I want to now move on to the kind of the setup. So if there are no questions, so I will be talking about these quantum nilpotent algebras, and for that I need I will need OR extensions. So as a reminder, so you start with an associative algebra A, okay, and an OR extension is just like a polynomial ring in one variable over A, okay, but where the coefficients don't necessarily commute with a variable. Okay, so if you want to use fancy terms, as a left A module, it's just a free module, and the basis is the powers of your variables. So it's kind of as a free module, it looks like a polynomial ring in one variable. But when you multiply coefficients on the right by the variable, you need to adjust things. And these are adjusted. I can see that you can see my pointer. These are compensated here by this. So if A is a coefficient, an element in the coefficient ring, and X is the variable, then if you want to move it to the left, then you change the coefficient a little bit, and there's kind of a remainder term, and these are controlled by an endomorphism of A and by skew derivation of A. I won't say much more than this. And this is what we call an OR extension. Okay, so it's just kind of a little deformation of a polynomial ring. Okay, now going back to solvable Lie algebras, the enveloping algebra of any finite dimensional solvable Lie algebra can be expressed in these terms in an iterated fashion. Okay, so an enveloping algebra solvable Lie algebra can also be written as an OR extension several times, okay, an iterated version of an OR extension. So you do the extension several times, okay, so it looks like this, but there's much more I can say. So first, all of these endomorphisms here are in fact the identity, okay, so there's really no skewing on this first part here. These derivations here that appear are just the adjoint derivation coming from the Lie algebra. Okay, and the number of steps that you need to do this in is the dimension of your Lie algebra. Okay, and if furthermore your Lie algebra happens to be more than solvable, for example, say nilpotent, then these derivations are in fact locally nilpotent. Okay, so this is a feature of the enveloping algebra of a solvable Lie algebra. Okay, so for these extensions, these quantum versions, so these UQGs, we have a similar description. Okay, so they're also expressed as an OR extension in several steps. Okay, Now, it's no longer true that these endomorphisms here are the identity. They're not the identity, but they're almost the identity. Okay, so they act semi-simply on the generators, on the variables. So they're scaling. They're just scaling the variables, and they're scaling by a power of q. So, for example, when q is equal to 1, this is the identity. Okay, so it's just perturbing the identity a little bit. So it's changing one eigenvalues into powers of q eigenvalues. So this is one difference. And there aren't many other differences. So it's still true that these derivations that appear are locally nilpotent. Okay, and kind of the novelty here is before the automorphisms were the identity. So of course they were commuting with the derivations. But now there's a q relation between the automorphisms and the derivations. Okay, so they commute up to a power of q. Okay, and this is one of the characteristics of this whole business. Okay, so why am I telling you this? Well, because this is one of the algebras that I'm looking at, but in fact, there's a larger class of algebras that has this common description, and this is precisely what a quantum nilpotent algebra is. Okay, so quantum nilpotent algebra, which has also been named a CGL extension, giving credit to Caen, Goodall, and Letzter, is essentially an algebra like the one in the previous slide, okay, that can be expressed as an iterated or extension, okay. But it comes equipped with some more information. So it comes equipped with the action of a rational torus. So this is, let's say, if you want to take this as a definition of a rational torus, okay. So this acts on your algebra in a way that these variables that you're joining in this construction are eigenvectors, okay. And the fact saying that it's a rational action is just saying that it acts on elements. So if I have an element in the torus, it's called lambda 1, lambda 2, lambda 3, say n is equal to 3, then its eigenvalues will be polynomials in lambda 1, lambda 2, and lambda 3. This is what it means to be a rational action. Okay, and so the extra condition is that kind of these automorphisms sigma here that are appearing here, in a certain sense, have to live in your torus. Okay, so they can be realized as restrictions of elements coming from your torus. Okay, so the torus needs to be rich enough to encode these sigmas. And this is essentially, there's a little bit of technicality, but it's not much. This is essentially what a quantum nilpotent algebra is. Okay. As I said, there's meaning to this. So again, the number of steps that you do the OR extension, this capital N. I mean, now there's no longer a Lie algebra involved, so I can't say it's the dimension of the Lie algebra, but you can think in your mind that that's what it should correspond to, okay? And it's equal to the Gelfand-Kirchhoff dimension of your algebra. And this is so nice that there's an analog of the rank of the Lie algebra. Okay, so you have a simple Lie algebra that has a certain dimension, but it has a certain rank. That's the dimension of its Cartan algebra. Okay, and this is something that exists in Q&As. Okay, so you can define the rank of a Q&A if you want. There are many ways to characterize it, and our results give you yet another way to characterize it. Is the kind of the rank, the number that appears here for the maximal torus. So the same Q&A can be equipped with different tori. Okay, if I take a subtorus of this one, so for example, okay, start to the n-1, where say the last entry is acting as 1. Okay, this would still satisfy in principle. This would still satisfy the definition as long as this condition were true. Okay, so you want to take you don't need to, but for what we're going to do, you want to take the largest possible torus acting on your algebra, and the kind of the dimension of that torus is what the rank of your Q&A is. So that's one definition. Another very algebraic definition is just you look at your presentation and you look at how many of these skew derivations are equal to 0. Okay? In general, this is not a well-defined number because you can present the same algebra in many different ways, and sometimes the deltas are 0, sometimes they're not. But with this kind of, if within this class, so if you follow these axioms, this implies that the number, you can still have many presentations, but in every presentation of your algebra as a Q&A, the number of skew derivations that are 0 is fixed, and it coincides with the rank of the largest torus acting on it. Okay, so again, you should think of this. You should think of this as the rank of the underlying Lie algebra, which doesn't really exist there. Okay, so that's the theory. Okay, so I want to make a few remarks because it will be more convenient for me to work rather with, instead of the action of the torus, I prefer to work with a Q grading because this gives me more of a connection with Lie algebras. So a rational action of torus like this is exactly the same thing as a grading by this free abelian group of the same rank. And the connection is that the eigenvalues for the torus are exactly the homogeneous elements. Okay, and kind of the grading are kind of the exponents in these polynomial way that the torus is acting. Okay, so instead I will be using always the skew grading, which is coming from the action. It's equivalent to the action of the torus. And I will think of the skew as the root lattice of some Lie algebra, which might not exist, which in general it does not exist, but this is the kind of the intuition behind it. Okay, so examples from what I said, of course, these UQG pluses where G is a semi-simple Lie algebra are examples of Q&As. You can go to symmetric X-Moody Lie algebras, for example. You can go to quantum Schubert cell algebras, which are these kind of, in a sense, sub-algebras of UQG plus, which depend on the elements on a chosen element of the Weyl group. Okay, but there are many other examples. Quantum matrix algebras, so several quantizations of coordinate rings of nice varieties will be Q&As. So it's a very large class of algebras. And it turns out to be more convenient to work in it, and it contains the algebras that we were interested in. Okay, so this is the scope that we'll be working on. And since, I mean, as I said, this is somewhat technical, and I think I'm going to show some mercy and not and skip over some of the technical details. I want at least to carry a running example, okay? And the smallest non-trivial example, I mean, the case A2 is already a little bit, it's already non-trivial, but still not enough to motivate what we're forced to do. And A3, so 4x4 matrices, SL4, is already a very complicated example, and it's good enough to illustrate what's going on. Okay, and I should say here in this case, type A is more complicated, for example, than type B for certain other reasons, or type C. Okay, I'll maybe mention it. So in type A, what do we have? So the rank of the Lie algebra is 3, and that coincides with the rank of the quantum nilpotent algebra. The dimension of the Lie algebra, well, it's just upper triangular matrices, so it's 4 choose 2, which is 6. The Weyl group is the symmetric group, and I need to choose think of it as a Coxeter group, and I need to choose a representation of its longest element in terms of simple reflections, and this is one of the many possibilities. Okay, and so this corresponds to this permutation that you have here. But this part here is what matters, and it's going to be relevant. So you're going to see, and this is what's really amazing, that even in the more general setup of a quantum nilpotent algebra, where you don't really have all the algebra laying around, somehow there's a hidden kind of Weyl group combinatorics that is actually very important. Okay, I'll get there. So for now, how would this give you a presentation? So taking this Weyl group, well, I could construct this presentation. You start with a simple root alpha 1, and this gives you a certain weight. So this constructs an element in your enveloping algebra that has that weight, and in this case, it just corresponds to the Chevalier generator E1. And then you do S1 applied to alpha 2. This gives you another root, which in this case is alpha 1 plus alpha 2. And we are able to construct, there's a procedure, for example, using Lustig automorphisms, but there are other ways. You can also use the Ringel theory with a Hall algebra. And this allows you to construct a kind of a root vector, which in this case is this one that has this weight. And you continue doing this in this fashion, and you construct your 6 variables that are going to be used to form your quantum nilpotent algebra, your Q&A. So this is the data that you need. Okay, and if you want, you can think of them, even though now this has nothing to do with really with Lie algebras because of these Qs, but this is more or less where they belong. This is how you can think about it. Okay.
Yeah, sorry, Samuel.
Yes.
The way you wrote it, x3 depends on x5.
Yeah, this is just, yeah, I know. Yeah, I know. I was hoping that no one would ask me that question, but it's just shorthand. I mean, I know it sounds circular, but it's not. I mean, you can define x3 in terms of it was just not to use too much space here. You replace your x5 with this element here.
Okay, so you mean that you can construct it and then a posteriori you realize that?
Yeah, and a posteriori you realize this. Yeah, but to make this short, this is how I wrote it. Yeah, but you're right. Thank you for the question. Yeah.
And sorry, if you use different writings of the longest word, you will get different elements.
You get different presentations. Certainly. Yeah, certainly. I'm going to tell you how I used this one, which was some reverse engineering, because a long time ago I had a paper with Stefan where, this is why I tell you that this is already a complicated case. That we, essentially the whole paper is working out this, case. And since I didn't want to redo calculations, I did reverse engineering to find out which is the composition of the longest element that gives me the calculations that I already have. So it happened to be this one. Okay, but if you do a different one, you will get different elements. Yes. Is there another? Thank you for the question. Are there other questions? Okay. So this is how things are going on. So this is how you construct in this case, how you construct this UQ SL4 plus as a Q&A, and this will be relevant. It's not just informative. This will play a role. Okay. So since I suspected that it's taking me much longer than I expected to get where I was, I thought that a third of the way through the talk I should state the main results to make sure that they don't get lost. Okay, so I'll tell you what the results are. So we will be working in the general situation of a Q&A. Okay, I'm calling the rank n, which means that it's graded by this free abelian group z to the n. Okay, and again, to make the connection with Lie theory, I'm going to say that if I have a homogeneous weight element, I'm going to call its homogeneous degree, I'm going to call it its weight. So this is just notation, like we do in Lie theory. It's the weight of the element. And well, Z of R is the center of the ring, okay, of the Q&A. And the thing that's interesting that comes about is kind of the dual of this root lattice. I'm going to call this sometimes the root lattice because that's what it is if you were a Lie algebra, if you were coming from a Lie algebra. So we're going to need the dual of this with respect to the center, so with values in the center, which is just since Q is a free abelian group, This is just n copies of the center. Okay, and for any element here in this Q check, I can construct a derivation, which is just a map that sends a homogeneous element into a certain multiple of itself. And the point here is that this central multiple is not arbitrary, but it does not really depend on A. It just depends on its degree. It depends on its weight. So as long so two different elements, if they have the same weight, I will get the same central scalar here. Okay. So these are the kinds of derivations that we're going to consider. Sometimes I will call them Eulerian derivations because they're kind of reflecting the grading. And I'm going to consider the set of all of these derivations. I'm going to call it theta q. So all of the derivations of the form theta eta, which is not a good choice of notation for reading, theta eta, but so all sorts of Eulerian derivations. Okay, and there is a little condition. There are a few conditions, not too many. One is that the Q&A is uniparameter. So you remember that in the definition of Q&A, the automorphism sigma and the skew derivation delta Q commuted. Okay, if I have, so this happens for sigma 1 and delta 1, this happens for sigma 2 and delta 2, and it always has to be the same Q, but it can be with different powers. Okay, so say more or less, if you're in a field where you could do logarithms, this is essentially not a restriction. Okay, because you can put any non-zero scalar as a power of the same thing. Okay, but if you're not, so this is what I mean by that. So it's a uniparameter Q&A. Everything will be powers of Q. There are no 2 or 3 or 4 different parameters. I'm also assuming, and this is really essential because our results are false if this is not true, that none of these generators coming from the Q&A is central. Okay. And there's a small technical condition on the center of the Q&A, which again is needed. And I mean, if this doesn't get too technical, I can more or less show you where and how it's needed, but to rest assured that it's a condition that is satisfied for all of these UQG pluses, except for SL2. And why except SL2? This is kind of obvious because what is the positive part of SL2? I mean, as a Lie algebra, the positive part is just a one-dimensional Lie algebra. So its enveloping algebra is just a commutative polynomial ring in one variable. And the same thing is true if you quantize. Okay, so if there's in your semi-simple Lie algebra, one of the simple algebras that appears is SL2. When you take the positive part, you will get a central variable. And you don't want that. So SL2 needs to be excluded from this description. Okay, so the result is that the Lie algebra of derivations can be described as the inner derivations direct sum with these Eulerian derivations. Okay, this is this other. So there sometimes we can use, and I might use the word central derivation, but remember, central can be a little bit deceiving because it could give you the idea that the central scalars could be arbitrary, and they're not. The central scalar depends only on the degree of the element, okay, that I'm evaluating at. So this is the result, okay? It's a uniqueness result, and so in particular, the first Hochschild cohomology, the outer derivations, is a free module over the center, whose rank is precisely the rank of the Q&A. Or if you want, the rank of the root lattice. So this gives also another way. That's not the purpose, but this justifies in another way how this rank does not depend on the presentation as a Q&A.
Sorry, Samuel, because when you explain, sorry to interrupt. Can you hear me?
Yes, I can. Yeah.
Okay. Hi. When you explain about the rank, I thought that the proof that the rank, the number of derivations that were 0 was of something of this type, that it was a cohomology HH1, but probably there is another proof before you computed the cohomology. So how
Yes.
can you say something about the proof, the other proof?
Yes, I mean, one other proof is, for example, the theorem that describes the automorphism group, where the n that appears there is precisely that same n, which is the rank.
Okay.
That's
Okay.
another way. That's another way of seeing it.
Okay. Okay.
Mm-hmm.
And
Thank you, Andrea.
Yeah. And this, so you have the Eulerian derivations that corresponds to a grading that is given by, so by what?
By the torus section.
Okay. Okay.
Yes.
Okay.
By the torus section. Mm-hmm. Exactly.
Thank you.
But which in the case when R is a UQG plus, this is exactly the same grade. This is the root grading of the Lie algebra.
Okay.
It's exactly the root grading of the Lie algebra, and the rank coincides with the rank of the Lie algebra. So all of these match up. Okay. But in general, yeah. So and we can describe this very explicitly. So if you take the Chevalier generators, okay, and well, if you consider these derivations, this is kind of ambiguous like this, but I guess we understand more or less what we're talking about. What I'm saying is I'm taking the dual of these simple roots alpha I, okay, and take the corresponding Eulerian derivation, which essentially it's this, okay. So it's the derivation that sends the Chevalier generator EJ to 0 if I is different from J, and it sends it to itself if I is equal to J, okay. And if you consider these kinds of and then you extend, this can be done. Although, I mean, from what we do, we don't need to prove that they extend. This comes already for free. So these specific derivations give you a free basis for this HH1 as a module over the center. Okay, and I stress, maybe at the cost of not of having to skip a lot of things, but I do want to stress this, that here these Eulerian derivations do send any element, any homogeneous element, into a multiple of itself. Okay, and I could have mentioned it before, I was lazy, but I guess now I realize I should have said it more specifically. For example, if you look at SL2, the positive part is just a polynomial algebra. Even if you quantize, it's just a polynomial ring in one variable. You know the derivations there. They're just central. They're just multiple. Central doesn't even mean anything in this case. Everything's central. They're just multiples of the derivative with respect to x. So, for example, there's a derivation that sends x to 1. And it's an outer derivation because there are no inner derivations. So it's clearly false. X does not get sent to a central multiple of itself. So this is kind of the root that we need to exclude. This is the case that we need to exclude. So it's important to remember that an homogeneous element will be sent to a central multiple of itself. And this will always be the case. Okay? So as I said, there are a few technical conditions on the center, but they're more or less natural, and they're satisfied by all of these algebras. I will always be assuming that Q is not the root of unity, but as I said, my field could have arbitrary characteristic. There's no restriction on the characteristic. Okay, and so this gives a very specific description, for example, in case of UQG plus, of what these outer derivations look like and what the basis is. Okay, and one thing that that's not written down, and at some point I did some calculations, and it was interesting, is to look at what this looks like as a Lie algebra. And it's interesting because I mean it's you see some kind of flavor, and this is not surprising, I guess, some flavor of a Witt algebra, but with many in many colors and kind of several of them being switched around. So it looks like an interesting Lie algebra, but yeah, we still have. I can't say
So
much about it.
sorry, the Eulerian derivations
Yeah.
do not commute?
No, these derivations, these derivations themselves commute, but remember that you need to take central multiples of them.
Yes.
And when you multiply them by two central elements, the Lie bracket will not commute because the derivation needs to act on these central elements, and they will act non-trivially on these central elements.
Okay.
They
And
do
you
not
get
fix the center.
sorry, and you get a kind of bit algebra, you said?
Yeah, it's not exactly Vit. It has some of the features of the Vit algebra, but it's more complicated because if you have rank n, it's kind of they're switching between one and the other. They're kind of going around.
Okay.
Between
Yeah,
them.
you have to tell me.
So you cannot isolate it, for example, as a sum of Vit algebras because they will all interact with each other.
Yes, I can see. But
So,
and then so you don't have for the moment the description. You don't know the. You said that you don't know the HHN for bigger n, no?
No, we don't.
Because if you have this algebra, you can look for representation. So
Exactly.
yeah,
I would
this
love.
is what
Yeah,
you're
I would
trying
love
to do.
Yes, I would love that. Yes, I would love that.
Great.
But yeah, I don't.
Okay.
But do you have an idea what the center looks like?
Yes. I know what the center looks like, and this is an important part because I kind of one of the big tasks in doing this, or in general for this these Q&As, is having a very tight control on the center. Because as you'll see, I'll be doing a lot of localizations, and when you localize, you keep changing the center, and this ruins everything. So we need to be very, very careful in how we localize so that we control what's happening to the center at every time that we localize. And that's the key. That's the key thing to do. Well, that's the key thing that we did, at least. Okay? So yes, we can say a lot about the center. So, are there other questions? So now that I stated the results, I'm going to start talking about the methods. Okay, and kind of the nice thing, and this is kind of, if anything to take away could be this, is that it turned out to be crucial to use a quantum cluster structure that these Q&As have. Okay, and this was developed by Goodall and Yakimov, and I'll say a little bit about this. So they introduced an initial cluster for these Q&As, and let me just show you here. What this means is that we have this algebra here. So remember that this is an OR extension, so there are lots of these derivations which are making the multiplication kind of nasty, complicated. But I can fit it between two nice things. One is this AQ, which is what I call a quantum affine space. So I have exactly the same number of variables n as the variables that I have here. So I have n variables, but instead these variables actually just Q commute with each other. When I say Q commute, it's a power of Q, some power of Q. So this is called a quantum affine space, and I can fit it in there. And the nice part is that if I invert all of these variables, and I look at what's called a quantum torus, I guess torus is being used here in many ways. They're all related. So if I invert these variables, and I get kind of this version of a Laurent polynomial ring, a skew Laurent polynomial ring, then by inverting these variables, it means that I manage to simplify these complicated relations here by doing changes of variables. So if any of you has done tricks with extensions and localization, you know exactly what I mean. By inverting certain things, you get new variables that have a much nicer relation. Okay, and so this allows one to put the algebra R in between this this quantum affine space and this quantum torus. And what's more is that these variables come encoded with a lot more information. And this is kind of where you get
Hello, I think we lost him.
Samuel, we can't hear you.
You can hear.
Okay, so your screen is moving.
Yeah,
Yeah.
there's a problem with
I
this.
just want to know about quantum calculus.
Can someone, I think he...
Okay, so let me explain a few words because I think it's more interesting maybe to explain an idea of how these things come about. Okay, so the idea of Gelfand-Setlin subalgebras is a way to find, you know, in representation theory, it's good to have large commutative subalgebras.
Samuel?
Well, because they yes.
Sorry, we lost your
Yes.
audio for a minute before you started talking about the Gelfand-Setlin subalgebra.
Okay. Thank you for warning me. Okay, so good. So what I was saying is that classically, Gelfand-Setlin subalgebras are just a way to find large commutative subalgebras of your algebra. Okay, this worked very well with Lie algebras, GLN, for example, even with the symmetric group. It has worked very, very well. And the idea, what's the idea of finding these large commutative subalgebras? In general, you get a chain of subalgebras. For example, if you're looking at symmetric groups, you can take Sn, inside of it contains Sn minus 1, inside of it contains Sn minus 2, and you get them all. Or for example, GLN, which inside of it contains GLN minus 1, which inside of it contains GLN minus 2. So you get this chain. And of course, there are many ways to put in GLN minus 1 into GLN, so you do it in a certain way, okay? And the way this Gelfand-Setlin process works is you start with the smallest algebra, and you look at its center, and then you look at the center of the next one, and you look at the center of the next one, and when you put all of these together, it's no longer central in general, but it will be a very large commutative subalgebra, okay? Now here, what is done is something similar, but since we're in the quantum setting, it's not reasonable to ask for the center, because that's asking too much. What we ask for is a normal subalgebra in the sense that the elements might not commute, but they commute up to a power of q. So there's I won't say the details, I think you can imagine. So there's kind of a normal subalgebra. And this is always something that I like to point out because it tricks a lot of people. So the normal subalgebra is a subalgebra generated.
We lost you again. I don't know.
Subalgebra will be normal. Okay. Also, do a large algebra that not all of its elements are normal, but it contains a lot of normal elements, and this is how you obtain these y's. Okay, the y's are obtained exactly in this way. Okay, the chain of subalgebras that you start with.
Someone, could you repeat how you obtain the y's? We lost
Is your extension. Okay, and you take that chain of subalgebras, and then for each one you start computing normal elements, until and this is how you get these y's. Okay, so well, this is what they are. They're what's called an initial cluster, quantum cluster, and the important thing is I mentioned here a coloring function. What this means, and I'll show you by example, is that to every one of those variables that we constructed before in the example with SL4, where we constructed x1, x2, x3 up to x6, okay, I can assign them color that goes between 1 and n, where n is the rank. Okay, and in an example, this is very easy to understand. So here's the example. Okay, so remember the first element x1 was obtained from this s1. So I will give it the color 1. The second element was obtained by this prefix here. You applied s1 to alpha 2. So I'll color the second element x2. I'll assign it the color 2. And then the third element comes from this initial segment here. And so I'll assign it the color 3. Okay, and you continue, and you get this sequence of colors. So this first one is the color of x1, this is the color of x2, color of x3, x4, color of x5, and the color of x6. Okay, so with Lie algebras, this is very clear because we have the Weyl group, and this makes sense. What's a little bit more surprising is that in any Q&A, you can always do this. Okay, even if you don't have the Weyl group, even if you don't have the longest element, there will always be a coloring function with good properties. There will always be a way to assign to every, if you want to think of it as a root vector, to every one of those OR extension generators, a number between 1 and the rank of your Q&A. Okay. And this coloring function comes equipped with 2 auxiliary functions, which in the talk I will only use the successor function. So maybe I will. So this one is needed for the proofs, but not for the results, for the main thing. So I'll focus on this, and this is just computing the successor in which way. I look at the element 1. Okay, here. When does it appear again? Well, it appears in slot 4. So the successor of 1 is 4. Then I look at the element 2, which is in slot 2. When does it appear again? It appears in slot 5, so the successor is 5. Then I look at the element 3. When does it appear again? It doesn't. So I assign it the value infinity. Okay, and we continue. For example, then this one, when does it appear again? It appears in slot 6, so I get a 6 here. And of course, the last 2 don't appear again, so they're both infinity. And these infinities are telling me something. These are the nice elements. Okay, these are the elements which will in fact be homogeneous. That's not asking much because the root vectors were always constructed to be homogeneous. They're homogeneous. They're prime in the sense that they generate a completely prime ideal. So if you prefer, they're irreducible. They cannot be factored anymore. And moreover, they are normal. So they might not be central, but they commute with everything in your large algebra. Okay, so this is what the successor function is telling you. Okay, so there are exactly 3 of these. Okay, and I can show you actually there's a procedure to construct these cluster variables. Okay, well, here you can mention the predecessor, which is defined the same way, but just as a predecessor. And whenever an element has predecessor infinity, it means that the y that I'm constructing just agrees with the x. There's no change. So the first 3 in the cluster are exactly what the x's were that we constructed before. No change here. But there's something interesting because the successor of 3 is infinity, so this tells me that this element is nice. Okay, nice in the sense that it's a Q-central element. It's a normal element. Okay, and in fact, I gave it the name delta 1 because in that paper long ago with Stefan, we had already called it delta 1. It was an important element. Okay, then for the first time, there's an element whose predecessor is not infinity, which means that I'm going to have to do something. To construct this y4, it's not enough to use x4. I'm going to need the predecessor of 4. Now, the predecessor of 4 is 1. So I'm going to need to combine x4 with y1, which in this case is x4 and x1. And then there's kind of a remainder term. But this gives you just an idea of how this is constructed for these things. And then you continue. So you know that the element 3, the element 5, and the element 6 are special because they are normal. And in this case, this means Q central. Okay, and here I just scaled this a little bit because to use the same notation from the previous paper, what we call delta 3, which is this element divided by Q minus Q inverse to the -2. Okay, so this very specifically is how you construct the initial cluster given your Lie algebra, if your Q&A is coming from a Lie algebra. Okay. And so in that case, it's easy just because you can just look at your longest element of the Weyl group, which you might have used already to compute the construction as an OR extension, and this immediately gives you the coloring function. If you have an arbitrary Q&A, then it doesn't come with the coloring function, but you know that it has one. You just need to find one that works. It's guaranteed to exist, and actually the theorem is somewhat constructive, so it gives you an idea how you can construct it, although it's better to guess because otherwise it's too much work. Okay, so is this more or less clear? So what's the relevance? This is the point. Okay, we need to look at centers. Okay, so what's the relevance of all this? And this is maybe the only point where I'm going to skip the other technical things, but here I'll just explain because it's easy enough. So let's start. So I think of this AQ, which is kind of, I think of my algebra as sandwiched between this quantum affine space and the corresponding torus. Okay, so these are the nice two things. These are the nice approximations of my algebra. Okay, so when I look at this, okay, and I pass to the torus, okay, this here is very nice because I can encode the Q commutation relations into a matrix, which records the exponents of Q that appear in the Q commutation relations. And it's very easy to see that the center, well, either here or here, but I'll focus on the torus because it has an advantage, which you'll see. The center of this torus just comes from computing the kernel of this matrix, seen as a transformation, if you want, from the free abelian group Z6 onto itself. So the big advantage is, I mean, the kernel of this matrix will be an abelian subgroup of this, and so it will be free of smaller rank. So we know that there's a set of free generators. Okay, there are many possible generators. Maybe you can choose some that are better than others, but you know that it will be free. And this is true if you're talking about the center of the torus. It will no longer be true necessarily for the center of this affine space. Okay, but for the center of the torus, you know, you compute the kernel of this matrix. You find a basis, and the spaces. So what does this mean? This is the element y3, and this is the element y6. So the corresponding central element will be the multiplication of y3 with y6. Here it is. So this gives me one central generator, and the other one is coming from here, and this is y5. So this means that y5 actually was already central. Okay? So the center of the torus is just the Laurent. Now it's really Laurent. There's no Q. It's commutative, right? It's just the Laurent polynomial ring in these two variables. So up to here, this always works like this. That's fine. There's nothing. It's just based on the fact that the subgroup of a free abelian group will be free. It works fine. Now, when I want to look at the center of the quantum affine space, I need to intersect the center of the torus with the quantum affine space. Okay? And in this case, it's obvious that it would just be the polynomial ring in these two variables. And why is this obvious? Because these two generators, Z1 and Z2, already live in A. Okay? For example, if instead of this one I had chosen a -1 here and a -1 here, it would still be fine. I would just consider the inverse. Okay? I would be in trouble if this were a +1 and this were a -1. Then, well, either I can find a better generator, or if I can't, then the result will not be neat as this result here. So there's some art to choosing these elements when you can. Okay. And so now the trick really is to look at the support of these central elements. And by support, I just mean the indices that appear here in terms of the cluster. So it's 3 and 6 for Z1, and it's 5 for Z2. So I look at the support, okay, and these numbers, 3, 6, and 5, give me a partition of the set of good indices, the indices that had successor function equal to infinity. Okay, so this is what we have for the moment. Okay, so the trick now, and this is really in the end, it's kind of, well, as you know from experience in doing math, there are certain points when you see, you really struggle to get there. It's very difficult. When you finally get there, you understand that, it had to be, and that math was forcing you to do it this way because there's no other way. And it's essentially, this seems to be one of these cases. So the trick is the following. Since I want to, the center of the torus is this Laurent polynomial ring. The center of the affine space is already different, but not too bad, okay? And I will be considering things in between. For example, my algebra R is between these two, okay? And I will be considering many other things in between, okay? So if the center is changing too much, then I lose control. So really the art in this thing is I want to invert certain variables so that the relations become nice. But I don't want to invert too many so that I lose control of the center. And the sweet point of this is to do that. Seems to be, it worked. So I want to say is to do this. I don't want to rule out the possibility of another way of doing it, but it seems so tight that this seems to be the way, which is the following. You take what I call pivots. What are pivots? They're kind of witnesses to each one of the central elements. So I go to the support of the first variable and I choose one witness. And I go to the support of the second central element and I choose another witness. Okay? If they intersected, I should make sure that the witnesses are different. Okay? And so I choose these witnesses, which I'm calling pivots. Okay? And I'm going to invert all of the variables except the witnesses. Okay? And by not inverting the witnesses, since the witnesses play a role in the center, I am not going to change the center. This is kind of the intuition. This is not a proof, but in the end it works. Okay, so the trick is the following. Okay, so this is the general case, but the general case is very much like the example, except here I can show you what the technical hypothesis on the center is. And the technical hypothesis is you have your torus, you get the corresponding matrix of key commutations, and then you look at the kernel, it's a free abelian group of a certain rank, you find generators, and these will give you generators for the center of the torus as a Laurent polynomial ring. Okay? The hypothesis is that I can choose generators such that kind of in terms of those vectors, so in terms of the kernel of that matrix, the entries in that vector, I can choose them so that they're all non-negative, and at least one of them is equal to 1. Okay, this is the hypothesis, and this is always true for all the UQ of G+. Actually, more is even true for there. So this is the hypothesis that I need. With this hypothesis, I have a guarantee that for the center of the corresponding affine space, I just get the same polynomial ring, so just not invert the variables, okay? And essentially, everything is controlled. So, as I said, I'm going to invert every variable except the pivots, okay? And by doing so, and I know that I'm going beyond my time, so I'm going to give you just a gist. By doing that, so this means inverting every variable except the pivots. This guarantees that when I do this in my algebra, it's enough to simplify the relations in the sense that if I invert those variables in my Q&A, that's the same thing as inverting them in my quantum affine space. And of course, they're variables in my quantum affine space. So there, with respect to those variables, the relations are very nice. Okay? And this somehow manages to avoid the center, and this is why I call it a separation of variables, because I'm able to keep all of the center outside of this mess, and everything is inverted is here in this smaller torus, which does not contain the pivots. Okay, so this will guarantee that this torus here is simple in this sense, and it guarantees that if I take any algebra between my quantum affine space and this specific localization of my algebra, the center will always be the same. So the center will never be changing. Okay. And just as a surprising fact, I won't show you the details to see where this is important, but this turns out to be crucial, that this difference is an even number. And this is, since it's so easy to say, I won't really say, this is the consequence of this. Okay, because remember that this center, it's a center of a torus, so it's coming from the kernel of a skew-symmetric matrix. Well, a skew-symmetric matrix, if it has odd order, will always have a non-trivial kernel. But this one doesn't, so that means that it's an even order. So the number of variables here has to be even. I mean, we proved this result independently, so this will force the total number of variables minus the number of variables appearing in the center is necessarily even. This is not a hypothesis, this is a consequence. And oddly enough, this is a very important thing. The proof does not work without this. Okay, and it's nice. As I said at the beginning of the talk, evenness is good because it leads us to geometry, to symplectic or Poisson variety. So it means that things are making sense. Okay, so at this point, I will omit details, but I'll just tell you the route, which is kind of the route that we often take, which is, we want to say something about the derivations of our algebra R here. What we do is, okay, let's take a derivation of R. Since derivations extend to localization, then I can see it as a derivation of this localization. And the point is that, can I say something about the derivations of this localization? Well, I can, but there's a previous step. If I had localized everything, all of the variables, there's a result, I think it's 2003 by Osborne and Passman, that tells me that derivations are inner plus central. And here it's really central in the sense that there are no constraints. Any central element works. Okay. Now, in our R hat, we didn't localize everything. And since when you don't localize everything, this result in general fails. Okay. But since we were very careful in localizing, we know exactly what the derivations are. So they're the inner ones, they're the ones which we like, which are these, that send one of these cluster variables into a central multiple of itself. And then there are some honest ones which exist, so there's no point in trying to prove that these don't exist because they exist. We want to show that in the end they will have to disappear. But at the level of our hat, they exist and they're here. Okay, and what are they? They're just partial derivatives. Okay, so now I'm not multiplying by z. So these central elements will force the existence of these partial derivatives, which is no surprise, right? When you look at derivatives of a commutative polynomial ring, this is what you get. Okay, so we control these. Okay, so we know this tells us that my derivation of R can be looked at as a derivation of R hat, and as a derivation of R hat, I know that it looks like this. But this x, so you're not deceived, is not in R, but it's in R hat. So it's not a central derivation yet. Okay, sorry, not an inner derivation yet. And this theta involves what we want and what we don't want. Okay, so there are two things that we need to do. I'm going to summarize them very quickly. First thing is to prove that because this comes from a derivation of R, we're able to prove that this element x has to be in R. And this is where we use, where the evenness of that number comes in.
Well, Samuel, we lost you again.
Is what is the proof with the x using our hat, where all variables on our hat minus 1.
Well,
And
we lost you for the last
yes?
30 seconds, maybe.
Okay. So summing up, it's just saying that we're able to prove that this element x actually does live in R, so it's an honest inner derivation. And so it shows that the remaining one, theta, has to also stabilize R, send R to itself. And this is the second. So here in the slides, I even show you how we can, I'm not voicing it, but if you want, the slides will be available so you can see more or less what the argument is. But the next argument involves theta. And the interesting thing is, I will kind of, it's already complicated in this example to say that things work as we want, but it's kind of a motivation. But I don't think I really have time to go through it. And the last blow of this thing is this. We are at a stage where we know that our derivation is an honest inner derivation plus a derivation that does the following. It sends the cluster variables to a central multiple of themselves if the cluster variable is not central. If the cluster variable is central, I can only say that it's sent to some central element. No restriction there. Okay? And the funny thing is that when we get to this point, I haven't used in the OR extension, I haven't used the derivations at all, the skew derivations at all. So up to this point, and this is already hard enough, what we proved is a result about a quantum affine space which has been partially localized. We localized some variables, we didn't localize the other ones. Okay, so in the case of the Q&A, if all of the derivations, so if I had a rank 0 Q&A, which means that all of the derivations are 0, then this is where we would be at. Okay, so really now is the point when we need to go back from the cluster variables to the original variables, and this is the point where delta, those skew derivations,
Samuel, can you hear me?
We lost you again. Es de ida y vuelta, parece. Ahí.
A ver. No.
No, pero ahí le podemos leer los labios.
okay. Okay. So sorry, my connection failed, but this is really the end. I'm sorry, I completely timed this the wrong way. So what I was saying is just that, I mean, it's this last part of the proof where it shows that actually the remaining part, the things which are not multiples of the variable disappear, and all of this really, I mean, it uses everything. There's no, it's really tight. We use everything that's available, and in particular, the maximality of this n is really important to show that these are just controlled by their homogeneous degree. This is kind of the effort of the proof, is to say that the value of the derivation, it's just depending on the weight of the element and not on the element itself. And so this is how we finish. And just so quickly, as I said in the beginning, we're interested in primitive quotients. So this is something we're trying to explore. But two other things is, I mean, we saw that it was so important, the cluster structure here was so important that we looked into looking at cohomology of quantum clusters.
We lost the sound again.
Yeah, I don't know if he can hear it.
That's it. No. Creo que no. Sam, ¿escuchás?
Here, I could disconnect from my iPad. Can you hear me now?
Yeah,
Yeah.
now yes. Yes, now yes.
Ah, the problem is, okay, I disconnected from the iPad. The problem is now you can hear me, but I cannot hear you. But it's fine. It's, let me see if in the settings, but so what I was saying while I look in the settings, what I was saying at the end is that this seems to be, I mean, cluster algebra structure here was really important. So and what we now have done shows that we can do things in the case of quantum cluster algebras. So this kind of opens up this idea, and it's easier, much less technical. So this shows that there's some potential here for this kind of stuff. And we were also successful with the Poisson. There's a version of Poisson nilpotent algebras, and their corresponding cluster algebra part, and this is also fine. So what we have difficulties with is the primitive quotients of Oppong. This is what we haven't cracked yet. So yeah, I'm sorry, I really timed this incorrectly. I had no idea with the time, but yeah. So.
No problem. Can you hear now?
So I think, yeah, I can see you saying something, Andrea, but I can't hear it. So let's see, what could I change? I can always connect again with the iPad. Just for this is the nice part of the talk, right, where you can actually relax and talk to the people. But rejoin. Oh, there's a button here. Rejoin. So I am trying to connect with there's yet a third of nowadays with technology I can also connect with my phone, and that's that is bound to work better. I think I will just do that. Nothing else, just to. Okay. Oops, sorry.
Okay, now you can hear, but now you can hear.
Can you hear me now?
Yeah. Yes.
Ah,
Oh,
okay.
thank you very much.
I should have used my phone all the all the way through.
Oh, thank you very much. That was very
We
nice.
did some, yeah. And
Thank
we
you.
see after the computations in the example that the results in general are very, very, very complicated. So I cannot imagine until I read them. Okay.
Yeah, yeah. I mean, yeah. The point, because it really is very tight. I mean, there's no. I mean, it just. It seems like there's nothing. There's no free space anywhere. You just are forced to do. Yeah, it's really, really very tight. It seems like, might be wrong, but it
Yeah.
seems like
Yes.
we're going through the only narrow passage that seems to be that we could find. It's
Yeah,
but
but
in the end.
maybe it's a first impression because with the Weyl algebra, at first I thought it was exactly very, very precise, but finally it generalized. So maybe later, yeah.
Yeah, but I'm still intrigued that, I mean, the fact that we can phrase the first Hochschild cohomology in terms of that torus, of
This
that
is
grading. I mean, the root lattice, in terms of the
this
root
is
lattice.
nice. Yeah, this is very nice.
It could be. Yeah, I wonder if the other cohomology groups could be expressed in terms of that. I don't know, because it seems. I don't know.
I don't know. Yeah, really don't know. Really don't
Mm.
know.
But yeah.
Okay,
So
we'll
by the way, Andrea, I was able
yes.
to watch. I wasn't in person because it was like 1 a.m. in Portugal. But I watched your other talk the other day on with Dotsenko. It was very, very
Yes.
nice. I was
Oh,
very
thank you.
intrigued with the connection with the incidence algebras, with the cohomology of the incidence algebra. So
Okay. Yeah, yeah, yeah. Thank
maybe
you, thank you. Yeah, I
maybe
really love.
sometime we'll be able to talk about it because it was very nice.
Yes, yes. I hope soon.
Yes.
So,
Yeah. Me too.
well,
Me
I
too.
send you a message later.
Okay.
Okay.
Thank you, Andrea.
Okay. Thank you.
So,
Do we have any questions from the audience?